In this video, I'm going to use the technique of substitution to compute three antiderivatives. In the first one, I'm going to choose square root of x to be the u. The method of substitution is a lot like the chain rule. It works well when you have compositions of functions. And so you want to think about what was your inside function for the chain rule. And we have e to a power. That power is square root of x. So I'm going to see if letting u equal square root of x is going to work. Now I have to compute my du. The derivative of square root of x is 1/2 x to the negative 1/2, and then we have to put on a dx. We can also write this derivative as 1 over 2 square root of x. Now I solve for dx. I can do that by multiplying both sides by 2 root x. That gives me dx is 2 root x du. Now I'm going to plug things into the integral, and I'm going to hope that the x's disappear. So we've got e to the u, and then I'm going to leave the square root of x in the bottom, and I'll replace the dx with the 2 root x du. The square root of x's do cancel out. That's a good thing, because now I have an integral that only has u's in it. I can bring the 2 out front, and I'm just left with e to the u du. The antiderivative of e to the u is e to the u, so we get 2 e to the u plus c. And then finally, I want to make sure my final answer has x's in it, so I replace that u with square root of x. In example 2, the inside function is the x squared plus 5. I'm going to try making that my u. The du would be its derivative, 2x times dx. So if I solve for dx, I get du divided by 2x. Now I plug those things into my integral, and I'm going to hope that the x's cancel out. So I've got a negative 3x over u to the 4th, and then I replace the dx with du over 2x. This looks good because the x's are going to cancel out. And in fact, when you're choosing your u, you can kind of think ahead about the fact that if your u has an x squared in it, there'll be an x in the du, and so hopefully there's an x somewhere else in that integral. So the x's do cancel out. I can pull the constant out front. The negative 3/2 comes out front. And I'm going to write that 1 over u to the 4th as a u to the negative 4. Now I can use my power rule. I add 1 to the exponent and divide. So I get negative 3/2 u to the negative 3 over negative 3 plus c. We can cancel those negative 3's out, and we're left with a 1/2 u to the negative 3. We can bring the u to the negative 3 to the bottom, and then finally I have to replace that u with the x squared plus 5. All right, one more example. The inside function looks like it's x plus 4, so I'm going to try letting u equals x plus 4. My du would then be 1 dx, so dx is 1 du. The integral becomes x over u to the 7th, and I replace the dx with a du. Now this time I can't cancel the x's out, and that's a problem. You can't have two variables in your integral. So I'm going to use a little trick in this problem. I'm going to take my equation for u, and I'm going to solve it for x, plug that in, and then see if I can do the integral. So if u is x plus 4, to solve for x I have to minus the 4. X is u minus 4. Now I'm going to replace the x in the integral with a u minus 4. And what's happened is I took something, an integral where I couldn't do the division, and I turned it into something where we can divide. Or another way of thinking about it is we can take that u to the 7th, we can bring it to the top. It becomes a u to the negative 7. And then if I distribute, I add the exponents. I get u to the negative 6 minus 4u to the negative 7. Now I can use my power rule where I add to the exponent. So u to the negative 5 over negative 5 minus 4 u to the negative 6 over negative 6. I'm going to bring those negative exponents to the bottom. And we might as well say minus 4 divided by minus 6 becomes a plus. Finally, there's two more things I can do. I can reduce the 4 over 6 to a 2 over 3. And I'm going to replace those u's with x plus 4. And there's my final answer.